So here you have an example of what an object may look like once we apply a structured illumination pattern to it. So we have an object that looks like this image on the left here. So you have here several patterns with different spatial frequencies. So this one has a range of spatial frequencies along this direction here. This one has a range of spatial frequencies along the x direction, but nothing along the y direction. So along y, ky is 0, and kx changes from, from in the middle here, the frequencies are high, and out here they're not quite so high, and so on. So you have different angles. You would expect the corresponding Fourier components to lie in this direction, in this direction, in this direction. So you would expect something like that. You have these very small dots here, so these are almost delta functions. So you would expect there to be a very high frequency content corresponding to these little dots down there, and then you have this pattern here, this ring pattern. So you can imagine what kind of things you might get. So you can if you take the Fourier transform of this, so in the Fourier plane, you would see perhaps a spectrum like that. That's exactly what you would see in the Fourier plane of the objective if we're not clipping yet. So this would be for a very large numerical aperture. So you see this frequency here maybe corresponds to, encodes this stuff here, and perhaps some of these features here. And then perhaps you have something around here, and that might be encoding for things that are down there. And so on. And then you have perhaps, if you want to look at something intermediate, so that perhaps you have this this frequency component, you see along this direction here, which will encode for these frequencies here. And then of course in the microscope, we clip with the optical transfer function, so only this much is passed through at the Fourier plane. So if I go now through the tube lens and synthesize from these frequencies, I get an imperfect image. And of course the image of the object will be degraded because I lose these high frequencies. So you can see, for example, that has resulted in this structure, these structures here not being resolved anymore. You can't see the individual lines. These dots, you can still see them somehow, but very poorly. And when they're close together, there's no way for you to distinguish them anymore, right? Because if they're closer than lambda over 2Na, their frequencies lie out here, and we can't resolve that anymore, right? Okay, so let's go on now, and let's now multiply the fluorophore distribution with a periodic function, with a sine wave. So the sine wave is shown here. It's a very fine frequency. There's a little zoomed in version here. You can see that it is modulated like a sine wave, but it's actually this pattern up here that you multiply this image with, the original image with. And of course the Fourier transform, so in real space it's a multiplication. So the original function, not this one, but the original object distribution will be multiplied with this. And the Fourier spectrum will be a convolution of this Fourier spectrum with the Fourier spectrum of this illumination pattern. So it's these three delta function that we've already seen. What does that do? So here's the original object. I project the pattern on. So let's put the first pattern on. So you can see already what happens, right? You can clearly see what happened. So by putting on a pattern that is arranged vertically like this, you can see now as I go across, I'm modulating some of these frequencies. And you can see for lines that are close to the arrangement of the illumination pattern, you can clearly see these low frequency moire fringes. So for this one, you've resolved it really well. For spatial frequencies that are arranged perpendicular to your illumination, you see nothing. So this modulation doesn't help you anything later on, because for that you would have to reorientate your illumination pattern to align with the spatial frequency of the information that you're interested in, right? So what happens in Fourier space? So of course, we have in Fourier space the spectrum of the illumination is 3 delta functions. K at frequency 0, we have amplitude 1, and we have half the amplitude at frequency k0 and minus k0. And so what we get is now a copy of the original spectrum centered around 0, and another copy centered here, and another copy centered here. So you see what happens? So I take a copy, place it here, take another copy, place it there, and then of course the OTF only transmits that middle part. So what you end up is this. I mean, you can see that this is messy, right? But you can also see that some of the high frequency stuff has now shifted into the passband. Or you see that high frequency stuff from this side has also been shifted into this passband. But the frequencies are all over the place now, right? So we need to tease them out. And the way to do that is we take another image, we shift by 120 degrees. I don't know whether you saw that shift. If I shift again, I don't know whether you saw that. Maybe that wasn't visible, but you shift the frequencies. And then so what you then do by taking 3 images, you have enough information to put these 3 overlapping spectra and shift them back to their correct place in frequency space. So you see now we have doubled the diameter of the optical transfer function, but only along the frequency that I'm probing. So if the vertical, if the stripes are vertical like this, then I would probe frequencies in this direction or close to that direction, right? But I wouldn't probe anything around here. To do that, I need to shift the pattern by this, and then do the same again. I take 1, 2, 3 images. I'm probing this part of the spectrum. Then I do the same thing again. 1, 2, 3, 1, 2, 3. And by doing that, I take 9 images and I get a super resolved image in total. So you see this here. This is the first direction of the pattern. This would be like that. And you repeat that. In all directions. So if you repeat it in this direction and in that direction, you actually fill out an OTF that is twice the diameter of the original OTF, and that leads to a resolution now that is lambda over 4Na, as we have described. So the trick is just to perform the unteasing information, the unteasing operation in Fourier space, and that you need big computers to do that because you're generating enormous amounts of data. So this reconstruction is hard work, but it's well worth it, as you shall see. How do I actually produce the fringes? And to do that, let me. Oh yeah. So what you do in practice is you take a laser and you project, let's say, a grating pattern onto the sample. And if you think about this, if you arrange the grating to be 1 focal distance away from the collimator lens, and you have the collimator length 1 focal distance from the back focal plane of the objective, then I get 3 delta functions here. 0 order, I get the -1 and the +1 order, and those will then pass through the objective lens. And in the Fourier, on the other side, you get plane waves coming out because, you know, if you have a focused beam here, a focused beam 1 focal distance away will turn into a plane wave. So you get 3 plane waves corresponding to k +1, k -1, and k naught. And they cross in the sample to generate frequency beats. I mean, I think what I might do is I might just quickly show this. So we have k1 going this way, k -1 going that way, interfering. And I quickly show this on the paper again, just so that this is clear how this works. So if I'm back here now on the paper presenter, please. Then if I have a direction X, let's say, and I have a wave coming in at K1 and another coming in with K1. So maybe I should have just drawn these to be the same length. Let me just start again. So here we have we have a plane along X, and then come on to this with K1 and K1 also from this direction. So it's just two plane waves. So a plane wave, of course, looks like this. So we have planes of constant phase, and they're spaced by lambda. And then we have, of course, planes of equal constant phase coming in from the other, and they come together on this sample here and interfere. And the interference gives, of course, I'm not drawing this very well. This should, of course, be all the same. I get a sinusoidal modulation along X, and this is really very much like Young's fringes. And I want you to think about this in the previous picture in the arrangement on the computer. The fact is, I have two spots. I'm arranging two spots to be in the back focal plane of the illumination objective in epifluorescence, right? So these spots emit spherical waves, so to speak. They go through the microscope. They are turned into plane waves. So you get one plane wave coming this way, so that'd be K1 coming from this way, and then you get K-1 from the other way. They overlap, and then you get in the sample plane where they cross, you get an interference pattern that looks like Young's fringes in some way. So I make this K-1 here and make that K+1 corresponding to the two orders. Okay, so we get if this is X, and we go up in, let's call that Z, then in fact you get planes of constant phase in this direction. So you get a plane wave anywhere in Z like that. And in fact, you have no modulation along Z with this arrangement. And now you can in fact make modulations that you can make arrange light so that you can get a modulation not only along X but also and Y, but also along Z. And along Z, so if Y goes out in that direction, so for this arrangement, perhaps it's arranged in such a direction that if these K-1, K+1 are in a plane ZX, then there's also no modulation along Y. So you think about that too. So these planes go into the paper like that. So if the plane in which these vectors lie is in the ZX plane, then you have modulation only along X, but the phase is constant along Y. You take any line along Y, it's constant, and any line along Z is also constant. But so if you want to rotate, rotate this pattern along Y, for example, or on the XY plane, then you just have to change the plane in which these two vectors lie, K1, K2. You just change it around, okay, to rotate the fringe pattern. But how can we actually generate fringes also along Z? And that you can do by putting another beam in, which I call K0. So that's going straight in. So that would be the zero order that we've also seen. So there's three spots. And I want to ask you what you think happens in this case. In fact, what you end up is you get a lattice, a light lattice, which is essentially get light and bright and dark dots arranged in 3D in that case. So you get modulation not just in X and in Y, but also in Z. And that really allows you then to get resolution enhancement in all three directions. So one exercise I want you to do is, for this situation with just the two beams here, can you work out what the fringe period is? And you can work that in two ways. And one is just geometrically by knowing that this is lambda here. and working out what the angles are, you can work out what that fringe period might be. And another is by just recognizing that a plane wave can be written as e to the I k dot r, and you just resolve the components of k along x in that particular direction, and so you get two counter-propagating waves, and you can work out what then the overall period is. And then I want you to at least think, not work anything out, but think, why would adding this beam in give you, or this plane wave, by putting that in, why would that now give you a 3D? I mean, it's kind of easy to see once you look at this in detail, and so on. But with that, I turn back now to my presentation, and so you see this here again. Essentially, what I'm creating is a plane wave going at k minus 1, and at k plus 1, and at k naught. And if I have all three beams present, 1, 2, 3, then I get this light lattice. So you can see the original light this way, and that way. So you get crossing illumination. So one goes that way, one that way, one that way, and that gives you this lattice. If you have only two component, k minus 1 and k plus 1, you see that the fringe pattern really is only in the vertical direction, as I've shown you on the overheads. Okay, so, and then you shift the pattern, and I don't know, this is animated here, so look carefully where my laser pointer, look first up here, so I move the pattern to the left, as you can see, and now I'm moving it to the right, and have a look what happens down here to the fringes. You can see how the fringes are moving as well as a result of this, where my laser pointer is down there. Okay, so that's the idea. There are electronic devices you can use, so-called spatial light modulators, and these are essentially just addressable pixels, and you illuminate these devices, and each pixel can be made bright or dark, and that allows you to image the patterns directly onto the sample. And you know, the way that this data projector works, that you know from lectures, it uses devices similar to this to allow you to put information in pixelated form onto a screen. So you see, you just changed the patterns, where they're reflective and non-reflective, on these systems. Okay, I'm not talking about 3D sim. Ignore that. That's not part of what I want to do. There are variants of this technique to gain more and more resolution, and these are advanced, so you can ignore that slide I just showed. It's not part of the examination. So on this, I just show you finally a few examples of things that we do in our own research with this technique. So what we've done here is apply this method to allow us to image individual molecules that cause Alzheimer's disease again. So these are these amyloid fibrils, and the point about this research is to test how does the presence of fibrils in the brain or somewhere else in the body affect the other proteins that are still floating around that are not part of these aggregates that cause Alzheimer's disease. So in Alzheimer's, you get proteins to start clumping, and they form these very regular fibrillar structures. And the proteins will fold and attach like Lego pieces into these long clusters, long fibrillar structures, and these then stick together and form plaques, and these displace brain cells. And so how that works is a study, of course, that is important to develop drugs and things like that. And so in this assay here, one of our students a while ago, he used SIM to Laurie Young. He used SIM to look at this aggregation reaction of amyloid beta, the protein that causes Alzheimer's. And what he's done is he's taken little fibrillar pieces of amyloid beta, labeled it with a red fluorophore, and he stuck them down with antibodies onto a glass cover slip, and then incubated the cover slip in a solution containing monomers of the same protein. And then he watched how these proteins latch on and grow into these fibrillar structures. And you can see this here on this movie. So you can see that the monomers are labeled with a green dye, and the fibrils that are stuck down on the cover slip are shown in red. And you can see, if you wait, you can see under the microscope how molecule by molecule these fibrillar structures grow. And so you can use this assay to test small molecule inhibitors or small molecule drugs. By putting them on there, can you prevent that aggregation reaction from taking place? And I want to bring home again, it's now possible with these high-resolution imaging methods to look at the kinetics of such biochemical reactions on a single molecule basis, molecule by molecule. And there are interesting things we find out when we look at these individual molecules. We see, for example, that for amyloid beta, the growth is asymmetric. So one end of the fibrils grows really quickly, and the other one grows very slowly. So here you have the original template, as it's called, the little fragment that you start off with, and then we have time going in this direction, and we have distance going in this direction here. And you can see how on this side of the template, the reaction proceeds really quickly. So you get very long fibers very quickly on this direction, and on the other side it grows slowly. And it turns out that actually that the two ends are asymmetric of these templates, and the ends act as catalysts, and they cause the polymers, the proteins that are not yet decided to latch on, they have slightly different catalytic properties and cause proteins to misfold, to continue this misfolded state, and more easily on one side than on the other. So one axis grows, one side of the fibril axis grows more quickly than the other. And those are things that just weren't known before one could image them. And so you can see this nice resolution that you get. We said, you know, going from 240 nanometers to maybe 120 nanometers is not such a great deal, but it is. So in this work here, a student, Meng Lu, in the group, in fact, he's a postdoc, he used structured illumination microscopy to look at what cells do once you expose them to these neurotoxic proteins. And you can see on this image here a cell, and the green bits in there are so-called microtubuli, which are essentially used by the cell to transport molecules along. And the pink bits on there are amyloid proteins that cause disease. And the cell's clearly taking those up. You incubate the cells with these, the cells take them up and they go inside the cell. But that's the sort of image you get on a normal high-quality fluorescence microscope. And SIM turns an image like that into this. And that is just with that factor 2 resolution increase, 2 along X, 2 along Y, and 2 along Z. Not only do you get massive increase in resolution, but you also get enormous contrast enhancement, because the technique cuts all the blur out. All the blurry light is gone. That's another advantage of it. So you get vastly superior images by doing this and learn more about what goes on in the cell. And finally, it is truly a live cell imaging technique because it's so fast. So here you really have seconds, and you'll be taking maybe 200 frames a second with our cameras to look at to expose at different phases, different orientations very quickly, and then we take corresponding images for all these orientations and phase shifts, and then we record. We take the data sets and we run them through these sim algorithms, and then you can actually see how inside the cell things are massively dynamic. These are images, you know, that were just not possible to have. It wouldn't have been possible to take images like that only about 10 years ago or so. So it really advances our way of looking at life on the molecular scale. And suddenly these cells, these tiny reactors turn out to be highly, highly, highly dynamic entities. And so here you see again. I mean, it's these little green lines here are again the microtubuli, and you see multiple cells are connected to one another. And what has been possible for the first time has been this is work by Meng again and by Laurie, who could show how these molecules are transported from cell to cell. And you can see how these misfolded proteins, these aggregates that cause Alzheimer's or Huntington's disease in this particular case, how they are trafficked along these information pathways here, so to speak, along these tracks, these microtubular tracks by motor proteins. So these cells are really working very hard to try and get rid of these foreign invaders, and if that they don't want inside the cells, so they try and deal with it. And of course, if the cell isn't capable of doing that anymore, you get more and more of this aggregation process that accumulates, and then that leads to cell death. And so here you see this again at higher resolution. So again, this is something you just wouldn't be able to see with any other method. So to finalize this lecture and this course, in fact, SIM is very fast. It's very flexible to be used. One of the great things is that for SIM you don't have any particular demands on the dye. I don't know whether I said it in much detail, but I certainly did for single molecule localization microscopy. You need to have a dye that you can photo switch. And if the dye isn't photo switchable between a dark and a bright state, you can't use STORM, and that actually limits the biology that you can do, because it has to be compatible with the dyes you have, and they're often, it's not possible to do multiple colors easily at the same time. With STED also, you need a dye that is depletable and works in wavelength regions that you can address with available light sources. SIM has no such demands. Any dye that works in normal fluorescence will work with SIM. It doubles resolution in every dimension and improves contrast dramatically. Disadvantage of SIM is it does not work well at depth. And the reason for that is you need to write these patterns, and to get those patterns faithfully projected into the sample, you cannot afford to have them distorted. If you distort these patterns because of scattering and other things as you go into the sample at depth, then the phases are no longer known, and you don't know exactly what the excitation pattern is, and then the method doesn't work very well anymore. And it is computationally very intensive. So a technique like this can easily generate tens of gigabytes of data per second. So it fills up a hard disk easily in a day of imaging, and then you have to deal with it and compute on this. And the computation is laborious. But of course it can be done on computers, and there are new ways of dealing with things with new methods such as machine learning and so on, all things that we actively pursue in our research groups. And so with that, I want to finish this lecture course, and I thank you for your patience going through this with me. I hope you enjoyed it, and I am of course available for questions at any time, and I'm also very happy to welcome you to see these techniques in action in our laboratories, and I would be pleased if some of you might be interested to pursue research in this, for example, as a PhD project. Okay, and with that, thank you very much.